The speaker today is Dr. Lee Deng from Microsoft Research, and Lee is my very good friend. Has been we're working on acoustics and speech for decades, and so he's the world expert in ASR or acoustic ASR, automatic speech recognition. And in fact, there's a research group at Microsoft in this area. So he's going to tell us the up-to-date information in the area.
Thank you very much, Jack. Yeah, so it's a pleasure to come over here to share with you some of the information that our company as well the industry is doing. So it's I try to inject some machine learning as much as possible, and also I show you some of the current view of the community, research community, as to what is the future direction for this this kind of field. It's a very practical field. It's reasonably mature compared with some other research field like image processing and computer vision. And everybody knows that technology isn't there yet. I mean, every time you make a call, for this airline reservation, it makes a lot of mistakes. And so people have the perception it's kind of mature field, but in practice it's not. And we all understand that there are a lot of limitations there. So one of the reasons I'm interested to come over here is to I really want to share with you some of the belief that not only myself but also a lot of my colleagues, in the leading in the leading research labs and the universities, they believe that human sort of capability of doing speech processing really would have big factor to contribute to the ultimate success of the technology. So I'm going to share with you some of the thoughts that I have. Acoustic modeling. So for speech recognition, there are three components. One is acoustics, one is language, and one is search. Three things all together, you get technology. Okay, I'm going to show you how. One single equation tell you all the story. Okay, so I'm going to be just as concise as possible to show you. So ignore this one first. Okay, so recognition. Fundamental equations. So if you read any textbook on speech recognition, this typically statistical speech recognition, this is just one single equation here. It's really simple. So first of all, this is the word you want to recognize. It's the word sequence, and this is the acoustic sequence. Waveform, whatever Fourier transform, whatever. So all you need to do is that as long as you know the posterior probability of what you have given the acoustics, and then you choose whatever word sequence that gives you the largest probability, and that's your solution. Very, very simple. Now, since this is continuous stream of information, right, and this is almost impossible to compute. I mean, no matter how you do it, there's no way you can do it. It's very difficult. Well, nowadays people think about some other ways of doing that, but traditionally, which is still the dominant technology, you break it up in terms of Bayes rule. Right? So that's the kind of things that everybody talked about yesterday. And then there's a numerator, or there's a denominator here. Right? But the numerator can be ignored just because the denominator has nothing to do with the search space. So it's a constant you can ignore. Therefore, you have this. So this probability becomes 2 probability now. And this is the probability of the sequence of the word. And that's called language model. And yesterday, I think Michael talked about language model. I think some other people also talk about that language model, which I'm not going to talk about this lecture. Okay. This takes another hour just to briefly tell you what it is. There are books written about this, and people are doing information retrieval. This is one of the very important approach to do that as well. So today I will concentrate on this. It's called acoustic model. So the reason why this is easier to compute than this is very simple. This conditional probability is conditional on continuous variable. I mean, it's just very hard to build the model that can actually do this. Whereas this model is relatively easier to build. Namely, for any word sequence, I mean, and you can think about it as consider a whole bunch of words, and for each word you can have phoneme, etc. You have a whole bunch of hierarchy of linguistic structure. For each of this, you can actually build the probability distribution. There's a simple by training. So, for instance, if you are looking at a sound called R, you can just take a measurement, take Fourier transform, do whatever you do, and you plot distribution. Right? If you plot them, it's with Gaussian, you consider it to be Gaussian, and that's all that. Right? But it turns out that for a word or for phoneme or for whatever linguistic unit, it's not as simple as just simple Gaussian. And as a matter of fact, since it's non-stationary, it changes the function of time. Right? So I'm going to show some diagram. You actually can see that the first part of this the word has a very different distribution than the last part of the word. Then then you need to have non-stationary model to represent this kind of acoustic model. And one of the major landmark in this whole field was the development of a model called the hidden Markov model, which I'm going to show a little bit about if you heard that word. That actually tells you that each sequence of observation can be represented by a multiple segments of distribution where the boundary is flexible. I mean, there's the whole power of. So if you know the hidden Markov model, you probably will understand. But I'm going to give some overview here as well. So that is called that actually is called the what's called the acoustic model for the state of the art. So all the systems that you are using, everything is hidden model in the line. Actually underline everything there. So one of the points I want to make here is that this kind of statistical view for recognition is very prevalent in entire speech processing, and also in image processing is very computer vision. They use that a lot of time, right? So give you another example. This is actually not the main part of this talk, and this kind of relates to the talk that Deng was giving earlier on. And his approach was kind of doing analysis, exactly how the streaming is done. Now, from statistical approach, we ignore all this, which may not be good. All we do is we still use a fundamental equation. So all it says is that in order to get clean speech, so Y is noisy speech. So if you do minimum mean square error estimate, and that's the solution. Well, that's called fundamental. So this is called conditional expectation. Actually, will give you the clean speech. So all you have to do is that you get probability right, and then you do this kind of computation integration, you actually get a clean speech. And actually, we pursue this approach a lot more aggressively than pursuing some other kind of more detailed analysis. So now, so that actually can be written according to this, and then by Bayes' rule you have this, and now you can see that. Well, so I'm actually going to give you a contrast between enhancement, how to get rid of noise, and how to do recognition. That's a similar problem. So in this case, you do Bayes' rule. In that case, you have to keep denominator. Otherwise, because you're not doing recognition to remove this. You're not looking for whatever Y that gives you something. Right? So this one has to be kept over here. Now, if you look at this part, you can see that. So this becomes the probability of the clean speech. And then you can train clean speech by collecting a lot of samples. And once you have that, this is available for you. Then, of course, you do, and then all you need to do, you do this kind of noisy speech model. And if it's an additive noise or whatever noise you have, that becomes very simple, right? So if you know the noise statistics, then you given the noise, this one is actually typically assume it's Gaussian noise or maybe some other kind of noise. If you know this distribution, and then you actually pre-train the clean speech model, which actually typically is we call a Gaussian mixture model or hidden Markov model, whatever. But since this is not dependent on word, typically you just use a very large mixture of Gaussian model. Typically we use 1,000 Gaussian. If you do that, you integrate them and you get clean speech out. That's the way we do it. so industry is, and then it's much easier to do. You just plug in the computer and everything come out, and then you get a clean speech. And then we use the clean speech and put each one, and then we get our recognized speech. So of course this one ignored a lot of knowledge. And then at the punchline of this talk at the end is that this approach is called blind, processing approach, and it gives you a lot of limitation. It doesn't allow you to incorporate a lot of human knowledge into the system. Yet it's a state of the art, and the limit. The only way to overcome the limit is many people actually agree that is to integrate good machine learning techniques with the human knowledge, and this is a big challenge, how to merge this together. So this workshop really just put these two together. So I'm going to share you with some of the thoughts that many people in the community are thinking about how to get is a psycholinguistic information, how to understand exactly in how all these words and all the linguistic units are stored in memory, how human access this memory, and that information will have implication to advance the state of the art now. So this is the introduction I just showed you. So one single equation that I show you probably tells everything, right? You don't really have to go over there, but except that equation doesn't tell you some of the little subtleties that I'm going to just describe. So recognition, a speech recognition, essentially to convert naturally uttered speech, which is X, into text, which is W, okay? And the meaning. And this is another one that I don't have time to go through. So it's not only to go from acoustic to speak to the word, but also to go from the word to meaning. And that's something that many people are working on, which is not It's not the topic of this talk. Now, conventional technology is statistical modeling and hidden Markov model. So think about hidden Markov model to be something like Gaussian distribution or mixture of Gaussian distribution, whatever, for the beginning part, for the middle part, for the end part. Maybe 3 or maybe 5 or maybe 20, depending how long the word is. Right? If a word has, well, typically for each phoneme you get 3. Well, that probably is good enough. And then for if you get a long word, which has about 10 phonemes, you get probably 30 states. So roughly it describes the distribution as a function of time. And that's what's called hidden Markov model. So the limitations of this technology, which people have many hacks to overcome this limitation. I'll show you some of those, and it doesn't do a perfect job. Is that, well, for noisy environment, you need to know how to deal with, and then the hack is the one that I showed you earlier. You do, conditional expectation, and then you compute that, and then fit that into the other equation. You get it. But it doesn't work well. I mean, it's okay, but it's better than without doing this. But it's still there are a lot of limitations. And also, a speaking style is very much. I'm going to show you some of the examples to show why hidden Markov model is a terrible model. And then there are a lot of things that need to be done. So every time you talk to a computer, normally you have to talk as if you can't just talk to the computer like you talk to the human. Right? If you do that, you just break down. And the reason why is because this kind of technology requires that you have reasonably rigid style. So you have to be slow, fairly slowly in your speaking style. Otherwise, computers can't understand you. And a lot of people actually don't know how to do that. They actually shout on the computer thinking that you will do it. And that breaks the system down even more. And once I show some diagram, you are going to show why. You are going to see why that will happen.
So is it because the training part doesn't include various speaking styles, or it is more fundamental?
There is more fundamental reason, yeah.
So it's not just the
correct. Correct. If your training data contain that, it helps a little, maybe help 20%. Okay. You still have 80% that is more fundamental. I'll show you some spectrogram display. You appreciate why that will happen. So also there's what's called unrealistic demand of training data. For example, in most of the standard large-scale recognizer, the amount of data now typically requires about 100,000. Wow. So some of the systems that I know, I mean, for government DARPA evaluation, typically they get about 2,000 hours of training. And then in some other systems, they go about 20,000, 50,000 hours. I mean, it's just essentially you have to cover all possible styles, including, I mean, hopefully you include some of the people who might actually overspeak, and you include people who are, casual in the speaking style, and also male, female, children, everything all together. If you don't have this number of hours, you just cannot train the model. So each model that we have, I mean, usually, you just couldn't. So this is one of the reasons why a lot of universities couldn't afford to do this kind of research. And I heard that last time when government sponsored some of the lab to the research, most of the budget actually they go is to build air conditioner to decimate, to make the heat. So it's very expensive, process to get state of the system there. It's a bit like search engine, right? Search engine, I mean, it's a warehouse. You have to build a whole warehouse in order to do that. So it's a very expensive process. It's what we call a build engine. And despite all this, it's still far below human recognition performance. And the train, and this is a very big train now. I mean, a lot of people actually thinking about now the technology has been more or less frozen for about 4 or 5 years, or maybe even more than that. The improvement actually is slow, very slow. I mean, the technology there, so people get one of the magnitude of higher data. People thought that the more data you have, the more bigger model you build, you can do better. But it's not the case. It's kind of plateau for 4 or 5 years. So the research community actually look into human speech processing mechanism, and also looking for better machine learning techniques that can hopefully provide some breakthrough in this area. Well, the problem with the speech community is that everybody is so much tuned into HMM. We know every single piece of HMM, how to tune this, and we just ignore. A lot of people actually ignore everything else. So if you talk to some old people in the student speech recognition, they have very limited knowledge about machine learning. Actually, sometimes I'll show you some of the things that as we go along. So this is the diagram that I'm going to show you to convince you why hidden Markov is not very good in terms of dealing style. Just to answer your question. So this is the one. This is my own voice. So I said 2 syllables. So I said this: yo, So this is a spectrogram. So anybody know how to read spectral? This is the time, this is the frequency, and darkness is the energy at that particular frequency time point. And this is the same word. Okay? I said yo-yo. So I said way faster. Then look at this. The same word. Ideally, you expect this and this to have the same acoustic information, but they are not. Right? If you speak fast versus speak slowly, you get very, very different acoustics. So the same class as in machine learning. I mean, typically in machine learning, you think that you have one class, you get observation, right? You produce the data. And typically you expect that the same, you get the same label, the data associated with the label should not differ from each other very much. If it differ away from each other very much and it gets overlapped with the other labels data, you get confusion. Just by definition. And in speech, that happens all the time. So I should show you the example like this. So this is what we call formants. Right? So the dark band coming down here. So this is okay. I say yo. Right? So this is okay. But this, look at this one. If I speak fast, yo. Right? Every time you speak fast, what happens is it doesn't really go down very fast. It doesn't have enough time to go down. Right? So after if you really force it to go down, you shoot all the way down here, but it's too fast. Right? So your mouth just doesn't have enough energy to go really fast, unless you know the other speaker doesn't understand you. Then you become very careful, right? And then you might want to shoot very hard. But if you shoot too hard, then you create different kind of patterns. You actually may deviate from your observation as well. So there are a lot of this is something we call speech dynamics. And this kind of dynamic, this does not get captured by hidden Markov model. The hidden model essentially tells you that for this sound, you have this distribution, you have this distribution, you have this distribution, 3 states, for example. Now for this distribution, it essentially averages out all this. Right? It just averages out because given a state in hidden Markov model, the output is we call ID. This is something that Mike Jordan talked about. Independent distribution, and that's not ID, right? Because correlation, it doesn't matter. I mean, even the mean becomes different, right? Because the mean in this part and the mean in different is different. But if you force the whole thing to be one Gaussian, you actually get average of this. And when you get average information over here, it just by definition, it overlaps with different kinds of sound. Right? So that's the reason. So this is yo, for instance. Now, if you look at something like another sound like it looks like this. If you don't consider dynamics, so by the very definition, the data overlap with each other depending on the different speaking style. So for a good model to capture all this, people always talk about is to use something better than hidden Markov model, or to make the state within hidden Markov model to be non-stationary rather than stationary ID. And there is a whole industry, over at least about 10 years working on this problem. But at the end, not very important result coming out, and partly because computation is extremely expensive at the time. So people at one time give up, saying, "Well, we know the problem, but but we just couldn't handle." But now people are coming back to think about the problem more seriously. The whole word distribution, yeah. People, long time ago, people used the whole word. Right? If you use the whole word, some of the problem may be overcome, right? But you train the whole word according to this. Well, that's the way it is, right? So this is the word. This is one word. So the word consists of many states. So that's exactly what we are doing now.
There are several phases, and in each phase it has different mean. So that in this word, the mean actually from a higher pitch.
Yeah, but that's exactly what it is. I'm telling you. So suppose this is one word, right? You get maybe think about 5 states. Right? In practice, you probably should more than 5 states. So the first state may cover this part, second state may cover this part, the third state cover this part, the fourth state cover this part, the fifth state cover this part. Right? And this is the same word, right? And the first state probably cover this part. And whatever you cover over here, and the first state may not be too bad. Right? The first state, this one and this one are similar to each other. That's fine. But the second state probably covers this part, and the second state here, there's nothing there. So you have to use some of the information from here. So you group this part of acoustic together with this part to train the second state model. Of course, you get huge variance, right? And then the mean is different as well. Once you do that, then it turns out that when you do this thing, slow speech and fast speech mix with each other, And then when you get a mean, which is in the middle, and that mean happens to be the same as another speech sounds average mean there. So by very definition, you get confused. So there are other problem people realize that. But if everybody have a fixed style, single speaker, the problem is not serious. Right? That's why you have to speak carefully. If you speak not like something like this, you screw. You know, just by looking at the data, you actually can conclude that that technology isn't good enough. Yeah.
I understand this case is very informative from the technological point of view because you're taking all the frequencies, and but probably cognitivistically, it's not really meaningful from the point of view of the speaker because we're stressing our approach in a certain way. That's we're not thinking of those qualities. We're thinking.
Correct. That's exactly the point. So next slide, I'm going to show you. So that's one of the reasons people think that incorporating the realistic production mechanism to give the right dynamics is one of the ways of solving this problem. So actually, I have some detailed result to show you exactly. But this all these models are very expensive to run. So that's graphical model. I'm going to show you some of them. So the kind of research, for the researchers, they work on a portion of this graphical model and the other portion of this independently. And someday people will put them all together. Once the computer becomes very fast, I think it probably will be reasonable. But anyway, so this is the whole point, the holistic view of this. And I'm going to show you how actually hidden markup can be interpreted as one approximation to this whole process. So when we talk about hidden markup for this, for all our experts in machine learning, we think about it as a generative model. Right? So when you have generative model, you want to get a joint distribution. Now, whenever you get a joint distribution, then that joint distribution hopefully will be realistic in terms of true acoustics, right? Not just train all the Gaussians. So if we think about this speakers process, the one you just mentioned, so the realistic generative model should be structured in such a way. First of all, you get a message, the word sequence that is supposed to be conveyed over here, right? And then you get a motor articulator control that actually moved this organ, speech organ, and then there is some dynamics that actually controls exactly how form will move up and down. So if this dynamic is modeled correctly, then it should be able to describe exactly why at a certain point it moves up, why at a certain point it comes down. Right? So that, and then of course through this acoustic it generates spatial waveform, and then you do Fourier transform, whatever you do. So this part is what's called the production mechanism. So what hidden markup is doing is to say that this entire dynamics that you just mentioned, so exactly how time moves and how that movement produced this, which also changes as a function of time according to the movement over here, is actually segmentally stationary. Well, that's what hidden markup assumes. So suppose you have maybe half a second speech, right? And then suppose you have about 20 states, whatever. So the hidden markup assumes that the movement of the articulator as well as the resulting acoustic generated from the sort of speech production apparatus has roughly 20 segments of stationary process. And in reality, this is continuous. Okay? So essentially, hidden markup is an approximation to what. So hidden markup also by itself is also non-stationary. Right? Every time you change the state, you change the distribution. So by the definition, that's also stationary. But the degree of that non-stationarity is very different than the realistic non-stationarity over here. And then of course, so the proposal actually that quite a number of people are actually, especially people in Europe, they're very like French. There are a few group. I myself actually have been working on that this model for a number of years. Is to say that we need to model both speaker and listener. Now for the listener, essentially, there is a processing going on. You get the ear and you get this one is doing Fourier analysis, right? And then plus you do some filter bank, and also you get well frequency, etc. And then also at the end you also do some some dimensional reduction, and this is all done. And then once you do that, then the standard fundamental equation view of speech recognition essentially says that don't worry about it. All this system is doing is to do decoding, just search whatever that matches the best, and that's not the right thing to do. Right? Now, from the human perspective, now for the real human processing. this is a hypothesis also as well. And there are actually two schools of thought, for speech perception people. One is to say that, well, whatever that goes into brain, triggers all the feature detector, and the feature detector, combine to get phoneme and to get syllable and then to get words. And that's one school of thought. And a lot of people subscribe to this kind of way. But once you have this kind of school of thought, it's very difficult to fit into statistical framework. So pretty much like what Professor Wang's talked earlier on. I think that's taking from that perspective. For the brain, it does all this feature extraction, and then somehow the linguistic pops up. Right? And then there's a good research that needs to be done to see exactly what statistical principle that can be applied to fit into that kind of framework. So another way that I myself have been working on, it's a very convenient way, but there is some theoretic, like a motor theory school, but this is the kind of modern view of motor theory. Motor theory essentially said that in the brain there's an internal model. So internal model actually is an approximation to this generation model. So this kind of model, I think some of the work done for motor control work done by Michael Jordan, I think many years ago, 15 some years ago at MIT, they actually assume this kind of model for the motor control. So I think in the speech, a small school of researchers actually advocating this. There's some evidence, but that theory has been overthrown, right? About 20 years ago. But there is a review of this theory based upon some recent literature that we see. There's an internal model. So this internal model sort of captures some essence of this production system over here. Now, when the human try to do speech recognition, what they do is that they actually use the internal model as a guide to match what the input coming from the ear, coming out of the ear into the brain, matches with the internal units in the speech. And then if you do the search, the argmax search in my fundamental equation, using this kind of statistical model rather than using hidden Markov model, that would give the brain with the capability of decoding speech. And this level is at a very high level, at the cognitive level. So if we take that view, we actually get a full, complete story about what human is doing. But of course, there are a lot of details that need to be figured out as to how to do that. Yeah.
So if you take this approach, so essentially, does that imply that you're going to have lots of internal models that are constantly running?
Yeah, correct. It actively does the search.
Actively seeking the input.
Mm-hmm.
So you see, at a time you find enough of a match to do an internal model and the input. Then say, okay, I got it. This is a word yo-yo, for example.
Yeah. So that
essentially you're saying that there's going to be, if you have 20,000 English words or whatever, that's going to be there's lots of models inside the brain that are constantly functioning.
Yeah, functioning. Yeah, it's actually functioning. Whatever matches the best, you actually capture it and then you output the word.
But there's also a principle of the sparsity, which means that the brain is actually most of the time a relatively small proportion of the cells.
So actually, so I think that would require some brain measurement as to when words hit into subject's ear, exactly what part of the brain is functioning. Right? So actually, I'm very much looking into some of the kind of measurement. I know other people are working on that. Yeah. So recently, I have been sitting in one of the working group in European. They take the funding agency just looking at precisely this issue. So I'm very keen to see what kind of measurement imaging result will come out. I hope that kind of probably will support some part of the internal model hypothesis. Yes.
You actually can generate speech simply while you're thinking. So your brain is functioning, and it has a stream of ideas.
Yeah.
So in your modeling, you don't necessarily have to have the
correct. Yeah, correct.
You can have multi-level processing of ideas, of sentences, of words, of phonemes, of tones, all happen together. Yeah. And so I think this idea, this simple model, or modeling at the signal level, like you described, does not help you understand how the words flow and how the ideas flow. And I think humans probably, you need really a very crisp model for that to get a very good process.
Well, but I do believe that the human sort of recognition system actually is working even if this is not working. So in the old model theory says that, well, you have to talk before this system is designed, but it really doesn't. I mean, there are a lot of evidence to show that.
I'm not talking about recognition now. I'm just talking generation of speech. Yeah, I agree with you that you want to recognize and you have to recognize what somebody else is talking. But if you are actually generating speech signal, that speech signal is generated not simply by a signal processing level, time series. It's generated by a sequence of words, a sequence of, and if you are aware of at the high level sequence, but you're not aware of the words that you're going to say, they come automatically at the lower level.
Okay.
Anyway, I have written a paper on this, which
I'll read to Okay, so actually, as far as I know, a lot of biological imaging research haven't been done. Yeah, we'll do that. Yeah, but of course, once you do that, you won't be able to build recognizable. So I will drill down individual levels. What kind of levels we are going to have this year, what kind of level we have here, and etc. And then we have to build mathematical model to describe them so that we can do computation. So once we do that, then in terms of decoding, it becomes almost impossible. So I have to do a whole bunch of approximation. so I'll show you how it goes. So give you some description about the two levels. Okay. So first of all, this image, you have to figure out how to encode the image or the message. It's not just aware of the phoneme sequence. If you do phoneme sequence, you won't be able to use that to control exactly how articulations are moving. Because articulation has, in order to produce sound, there are several layers, right? So there's actually a recent theory in linguistics that actually says that to produce a speech, there are roughly about 5 or 6 parallel channels that's going on. So lip is one channel, and the tongue is one channel, and also jaw is another channel. And also glottis is one channel, and then velum is another channel. About 5 channels roughly. Now each of these channels has to be controlled, it's independently controlled by the muscles. Now to do that, you have to encode original message in terms of these 5 layers. If you just use the phoneme sequence, you have no idea how to control it, you're not going to do that. Right? So this is one of the issues I look into very carefully. And the linguistic theory, actually Chomsky theory. In 60s, he wrote a book, Some Pattern English, essentially proposed that the coding of the linguistic message is based upon these kind of independent layers. And so this theory just perfectly matched with this kind of theory. So what I did is that I actually look at this phonological literature. And then actually I designed for different languages. At the company, we have fair amount of freedom to do kind of design. So for different languages, we actually designed that kind of inventory to fit in this kind of production model. And then, so this is a summary of this. So that's what's called distinctive feature model. Right. So this is actually this is the linguistic theory that current speech recognition people have no idea about the importance of. They just look at this, they say that, well, forget about this. And the phoneme is good enough. A lot of people think that way, still they think that way. So I'm one of the guys trying to convince them to go and understand this feature geometry because it has implication in terms of this overall theory about human production and perception. So I'm not going to go through detail except to mention that this theory at a certain level will really explain why certain sounds get deleted and certain sounds get modified when you speak in a different way. And that's, there are a lot of examples that show you need to have that one in order to deal with the variability. Whereas if you use the phoneme, very often when the speaking rate picks up, part of the phoneme will get deleted. Sometimes people say, well, how come? So dictionary become incomplete. So this one theory actually helps you to do that. And the lower level, this part is what's called phonetics. So phonology and phonetics in this level is actually in a distinct, in a different phase. So this one actually tells you how this control unit defined by the distinct features can be used to control the dynamics in this system. So actually for this system, I use a linear dynamic system to do that for each state. So every time I got this particular distinctive feature, I actually use that as a control unit to drive the linear dynamic system. That gives you only one single state in Hidemaker model. So in this entire model that I'll give you some more detail in a few minutes. We still have high-level Hidemaker model, but each state is not just Gaussian distribution, but the entire dynamic system that takes into account the feature that controls the dynamics. And the dynamics continuous in Articulatory, going from one state to another. And for that reason, Hidemaker state become dependent on each other because of continuity constraint you have to enforce in there. You can see that the theory gets very complex, so we're actually waiting for a lot of very powerful computer to solve this problem. So this will give you some picture, like, you know, in order, the current speech recognition system encode this word in terms of 10, that's it. Now for this one, there's 3 hidden Markov model states, 3 states, and maybe about 20 some states altogether that describe all this. So you get about 20 HMM states, and each of them has a few mutual Gaussians, and that's all it does to represent this entire thing as an acoustic model. Now, according to this theory, a lot more complex. I believe that's what human brain is doing. First of all, each the phoneme is represented by a few distinctive features, up to 5. For instance, this M, you know, you have something, you know, what's called labial closure, you know, because your lip is closed, right? And then now for Z, you get a constriction at particular location in the vocal tract. And for N, you can see that the nasal is closed. So you describe the physical properties of the production. Now, once you have that, the important principle in speech is that they are asynchronous with each other, and that accounts for some variability. And then once you have that, this becomes the control region to drive dynamics responsible for this sound production. So you get a dynamic. So essentially, you get 5 levels dynamic system running in parallel, which are asynchronous with each other. And then, of course, I have graphical models to represent this. And then I need to solve all these inference problem and then estimation problem. So that shows how the phoneme sequence gets expanded into multiple streams of asynchronous process from each other. And this is the so that for that particular system, this one becomes the dynamics that goes with each other. So if you look at this, it's very, very different from HMM, what HMM gives you. Okay, so you have this continuous dynamic going on, and that actually accounts for all the difficulties I mentioned earlier. Now, once you have that, so I'll show you this a graphical model that represents most of the things that we talk about. Here is supposed to have 5 levels. So at that level, it's really supposed to be factorial HMM. Right? So I just find the factorial HMM is just perfect representation for representing these 5 layers of distinctive feature model. Actually, it turns out that the standard factorial HMM theory doesn't actually fit this one quite well, because they don't really provide any constraint, whereas in speech there's a lot of constraint. If you have constraint, you can do computation much more efficiently. So this is something we're thinking on. So now for each of this state here, so this is now for standard HMM, when you get a state here and then you come down over here and that's it, just 2 layers. So this one would be considered to be hidden HMM. Wow, there are 3 hidden layers. Huh? So 1 hidden layer is a distinct feature, and then this is what's called the target. So for each distinct feature, there's a correlate with target dimension, and that tells you exactly where the articulatory, the movement have to approach. So it gives you the target, spatial target for the articulators, and this is the hidden parameter we need to estimate. So there's a parameter associated with each of this, and this is the articulation. So to go from here to here, we have dynamic system, linear dynamic system, which is controlled by the parameter from here. And then to go from here to here, we go from articulation to acoustic the conversion. And this part is very difficult to do. It's nonlinear, highly nonlinear. So if I give you the position of the articulator, like tongue in this position, lip in this closed position, and velum is open, you have that as a vector. And how do you and once you have that vector, pretty much acoustic is determined. Right? All you do is that you run simulation, and then acoustic come out, and then you do Fourier transform. And I have no idea how to do that, in the principle, except to use a neural network. So we use the multi-layer perceptual neural network to represent the relationship between this and this. Okay. So in other words, the conditional probability of the observed. This is always the observed acoustics, which is X in my earlier slide. Given the articulatory parameter, this is actually. So this is actually is the nonlinear function of this in the neural network plus a random noise. That's all I do. And well, this is pretty much what I do. Now, of course, this part actually is a noise. So so this is clean speech produced from this model, general model, and this part would be the environment noise. The environment noise has typically 2 parts. One is additive noise, and which changes the function type. So we use the nonlinear states over here to represent non-stationary noise. And also we have this channel, which is a convolution. So the one that we talked about earlier, which is called the reverberation. and reverberation doesn't change because one single room, but the room acoustic doesn't change unless you move your head a lot. If you move head a lot, this one should change as well. But typically we assume it becomes too complicated. So we fix this one to have convolution. So essentially to go from and this is the observed noise speech. So we have the distortion from the noise as of the channel on the clean speech to produce this the noise speech. So this entire graphical model essentially gives you 1, 2, 3, 4, 5, 6, 7 layers. Hopefully, brain probably has so many layers to deal with all these difficulties. And the hidden macro actually is 2 layers. That's it. Okay, well, this is a diagram. Well, I'm not going to have time to do this. Is a diagram to show you exactly how these individual layers go. So this is actually the phoneme sequence, which is put into linguistic meaningful term. And this is articulate dynamics. There are 5 of those, each controlled by one of the dot over here. And then there's a neural network to go from here to here. And then, well, these are all the detailed structure. And then we go probability search that simulates internal model functioning. So decoder, I'm not going to go through this. So decoder essentially tells you that this part has 2, the listener part has 2 components. One is what's called reception. So for auditory processing, to me, it's a pre-processing. And once you go down to the decoding internal model, that I call the cognitive decoding. I separate them. Otherwise, to me, the auditory process is a very simple process. It's just, essentially, it's independent of what linguistic unit you have. So it does Fourier transform, it does filter bank, it does male frequency. High frequency get ignored more than the other, and also it does some compression. So everything is done. It's a very mechanical process. I mean, you don't really have to do a lot of complicated process. And then the difficult part is this part, cognitive perception. That's much more difficult. But this probably consumes all the energy in the brain to do this. So essentially, what it does is that it uses, in graphical model view perspective, for machine learning particularly, this process, decoding process, essentially uses the graphical model as the underlying model, and then you do decoding. You do inference. So essentially, inference algorithm in the graphical model that I have really, so in this theory, that operation for doing the inference on the linguistic unit, using whatever observation you have, in this 7, layered model, essentially constitute the human cognitive perception. Right? And the assumption, of course, will be that, when humans are doing, children are doing language acquisition, they gradually build up that internal model. And the reason why the children take a while to learn is just because that is the time that this internal model is gradually built. So, well, of course, we need to have some research to show that the kind of process of acquisition essentially somehow gradually set up the synapse connections in such a way that some of the major functionality of the protective system somehow is encoded over here. I have no idea what it is. Hopefully, I'm looking. I really would like to look into some of the possible measurement to see whether some evidence may be in place to support this kind of model. Now, there's a very important, according to this model, there's a very important element which is missing in current recognition technology. That's called speaker-listener interaction. Okay, so the interaction in that model, interaction is natural, right? Because every time the listener is listening to the other side, internal model is adjusted according to how much he understood. If he doesn't understand it well, he sends information back to the speaker, and the speaker understand that. Well, typically, for human communication, then speaker become more careful. So especially for foreign accents. So when I was teaching many years ago, usually my student told me the first lecture I gave, they have a hard time to go through. The second lecture, no problem. So it takes a while. So I typically have to slow down in the beginning. And then after a while, I get to know each other. And that kind of interaction is totally missing in the current speech technology. There's no place to incorporate whatever the kind of interaction there is into the system. Whereas in this model, this is a natural part of this, part of the system. So there is an online modification of speaker's articulatory behavior based on listener's decoding performance. If decoding performance is bad, then speaker really slow down. And that is reflected in the adjustment of one of the parameters in the model. But anyway, so I'm just going to skip that quickly. So this is one of the things that I did simulation of. So this actually is is the formant. It's actually formant actually is correlated with the articulatory structure, right? So in other words, once you get the articulatory movement, then it produces the acoustic, and the acoustic has many attributes. One of those is the formant. So this actually is the decoding result. So in other words, I was running that model given the clean speech, and for clean speech, I do the inference. If I do the inference on the articulatory level, then I got something similar to this, and then you actually track acoustic quite well. And then using this, once I track this, I use neural network to synthesize speech. I got something virtually identical to the input speech. So actually, so most of the things I run, so it really shows that neural network is doing the good job, and also shows that this dynamic system algorithm is working well. And also, I did some speech recognition in the small scale, and I got some recent. So that's another synthesis result. So what we call a model synthesis capture. So all I did here is that, so this dotted line here is the real data. So I use this data to do decoding on some of the parameters in the model. And then once I got that, I run neural network backwards, and then I got something very, very close to what it is. So neural network is really doing a good job over here. And then I was, let's see. Well, so this is one part of the talk. How much time do I have?
5 minutes.
5 minutes. Okay, so I'm going to quickly go through here. So there are a whole bunch of other issues related to the technology. Well, I talked about the speaking behavior already, and I talked about this one already. Well, actually, I don't have time to go through all detail. Well, I have a few slides to show you how to deal with this kind of environment. These are all in the graphical model. I did. So a lot of work that I did is that I incorporate that part of graphical model, and then the upper part is much more complicated than the lower part. You know, acoustic part is, noisy part is relatively easy. So I'm going to show some of the result here within the next 5 minutes to see. And then when I do this kind of noise represents, I actually freeze everything up to be key to my model, so I can run experiment. Otherwise, I just couldn't do all this. So what do I have here? So there are a whole bunch of issues here, like prosody, accent. These are all encoded in the upper part of the model, which actually I haven't actually started looking into that so far yet. So probability generative model. Let me see. So this is the one. Yeah. So this is the summary of the one I told you earlier. So this is the phonological states. It gives you the pronunciation model. And this is the phonetic knowledge. Phonetic correlates, which is expressed in terms of the target parameter. And this is dynamic. This is the clean speech right here. And this noisy speech as observation. This is non-stationary environmental noise, and this is true state noise, environmental noise. So you have dealing with the time varying noise. You need to have fairly complicated noise model here, which we actually have. So two case study. Let me go through here. So let me spend maybe 2 or 3 minutes talk about this part. Okay. So this part. So this part of the graphical. This work is all done, and then we got a really fantastic result, assuming that everything up here is hidden markov model. And then this is I spent the whole year working on this. And once you use the HMM over here, anything you do here can go to product. It's pretty easy. And if you go something more complicated than hidden markov, it's very hard to put it in place. So I show a few some result doing this. So if you look at this graphical model, all you need to do, for those of you who are not familiar with graphical model, each arrow here shows you conditional dependency. So when you have arrow going down here, then all you need to do, you have to specify the conditional probability of this variable given this variable. So I'm going to show you how to derive that kind of variable here. So next few slides to show you how I can specify this conditional dependency and how I specify this conditional dependency. Once you have that, you can do all the running just standard graphical models to get all the results. So to compute that conditional dependency, you need to get some physical model as well. So everything I'm doing here is physical, by physics. So it's doing mathematics and the physics, and then of course, there's some biology over there. So in the time domain, you get convolution for the channel and plus additive noise. Now, if you do Fourier transform, you do this, and then you do energy. You have this, you have this, you have this cross term. And then once you have that, let me skip all this.
Noise is not independent of speech.
It's not independent speech, correct? No, I don't have that. In practice, it's not. Typically, it's not. If it is, then we have another feedback. But some of the noise is some of the articulatory behavior depends on noise. If noise becomes large, no idea how to build that one. At one time I did put this feedback over here, but I got intractable problem in graphical models, so I kept give up. But this is interesting because in realistic scenario, speaking behavior may get affected by noise, and this is nobody there even to touch the problem so far. So so once you do that, you can see that. So this filter-based stuff is all done, built down here. Let's see how do I due to the time. Okay, but it's okay. So let me see. So it's trust all this observation. Okay? So this is the what's called the capture coefficient. Okay. So this is the speed the feature we actually go into the recognizer, and then that's noisy capture coefficient, the MFCC, noisy MFCC, and X is clean speech MFCC, and going through all this log. Remember, you do Fourier transform, you take the log, you do cosine transform. We do them all together using this the model, linear model distortion. Now in the capture domain, it becomes nonlinear. And how nonlinear it is this much nonlinear. So this is like the program in our program, our computer program. So this becomes the capture of the impulse response. This is the capture of current speech. This is the capture of noise. And then you have this nonlinear relationship. So once you have that, then you can get conditional probability out. Right? So once you have that, all you do is that you get so you have conditional probability of noisy speech given clean speech, noise, and channel. Then once you have that, you specify that conditional probability. So you fix that part of the graphical model. And then once you do that, you do your decoding. So everything becomes mechanical now. So it becomes fairly complicated. So it looks like this. It's a Gaussian. So we did that. And then of course when you do that for nonlinear, how we do? We do Taylor series expansion. And another piece of work we did is that we used the variational learning, the one you heard from yesterday from Michael Jordan, and both approaches give similar kind of result. So after we go through all this that becomes the this becomes the formula to get this clean speech. Now when you do that, and then I'm showing some result, and the result is it really improve the recognition dramatically, which if you're not in the field, probably you won't appreciate all these numbers anyway. So this is the top keynote talk I gave last year. So people in the speech, they actually understood exactly what it means. So there is a fair amount of information gained. This is recognition accuracy using the standard noise model that I showed you earlier, and this one, the new one that includes the face information there, the one I showed you earlier. So we get a very high recognition accuracy. So the second case study gives you 2 more seconds. Okay. So this study actually deals with this part of the system. So I freeze this part. When you fix it all together, it's just there's no way we can do that. Well, actually we do a lot in some intern. When intern come over here, we say, well, why don't we work on this part? And they work on this part. So we get several pieces together. So someday I myself have to put it all together. So this project actually deal with clean speech, but it deals with speaking style. Okay, I'll show you some of the result here. So this, let me see. So this is the simulation to show that. So this is the E-R-E. Okay. So this also E-R-E. If you speak slowly, you get something like this, right? If you speak fast, you don't have enough time to reach that, so you just skip this. So you can see that you get a very different acoustics, similar to the kind of things that I do. Now this is now this. So one of the things you can do is that for different duration that you have, you can plot exactly what this formant looks like. Right? So if duration becomes shorter and shorter, you can see that formant move. And this is an extremely important phenomenon in speech. So model prediction goes as follows. The speaking rate becomes faster and faster, then F2 is moving up and up, and then F1 is moving down and down. So certain parameter actually changes. So most of people think that what speech, when you say it's that's it, right? No, if you speak fast versus slowly with different contexts, you have very different behavior. This is the nature of the data. So now you can see that, and this is another. Well, this is actually the measurement from the literature. It shows the same kind of behavior. Right? So this is the model prediction. This is the measurement. So how the sound, what is the data associated with each class, really depends upon how it's spoken. And this is kind of very common knowledge, and that's one of variability that plague everybody. So this one shows that when you speak clear and slow, okay, you get a space looking like this. Now 3 sounds that are separate apart from this much. Now, if you speak fast in the conversation style, everything shrink down over here. You can see that everything really, really shrink down there. It's much, much easier to confuse each other. That's one of the reasons why, for casual speech, you get much, much higher recognition rate. And human is okay. Human has no problem whatsoever on this. And then there's some theory. I mean, the model that I built actually takes into account the human's capability. So the assumption is that human can extrapolate the information. Right? So even if they're very close to each other, and the human, it knows that you are small, and then extrapolate out, so it becomes separate apart. And the model that I built actually built that structure into the model.
Well, sometimes even humans have trouble if people slur.
Yeah, if people slur. Okay, yeah. Correct. And that's because your space is small. Sure. So that, the only way to explain is that the extrapolation capability has to be trained. So after you heard that for a while, and they train the extrapolation to make it separate apart. And the same thing that happens for this vowel. But for some of the vowels, especially for this neutral vowels and the squeeze, it's much small. So look at the discriminant space, it just becomes so close to each other. Just by definition, the sounds get confused more with each other than otherwise. So I'm almost going to finish this one. And then, well, let's just show you. This is actually the very best result that I got here. Well, I don't know anybody is doing timid experiment. For anybody who is doing speech timid is one very standard that everybody uses that. So the state of the art HMI get this accuracy. That's all you can get for phoneme recognition. And human, I heard that only get about 80% for this. Yeah, because that label has a very fine phonetic label into it. And then we use this model. We move the model that I show you. Actually, we move up to about 75%. That's all we can get. It's very hard to move in. So there are a lot more research that needs to be done. And then actually last time I went to MIT to give this talk, and they are the group who actually produced the data. And then the guy who actually did this data collection said, maybe the remaining is labeling error, just to make me feel better. But I do realize that the model we built still has a lot of limitations. So there's some progress, but a lot more nothing. Well, one of the things that we did early on was that all the decoding algorithms that we did. I mean, for those people who are actually expert in the graphical model, like Tony or those others, if you look at this model, the first time I present this model, I have no idea how feasible it is. And then we got a lot of experts in our Microsoft research. They look at this model. Are you sure you want to do this model? And then I said, well, I mean, if it's right, I want to do it. I mean, even if it couldn't be. I always take the philosophy that make a model right first. Right? Just like Michael Jordan talked about. Yesterday he talked about modeling part, and then all the algorithm comes second, and then you can always use the approximation to do it. Unless it's in principle you cannot do it, then I want to go back and simplify the model. That's also philosophy. And also I believe computer will become faster and faster. Now it couldn't do it, but algorithm-wise, that model is intractable. Well, I know that. So we use the variable learning. We use a lot of approximation from machine learning to do this. So we get a human inspired model, and then we use machine learning inspired technique to solve them. So hopefully there's a good mix. Okay, so this is the final slide that I show. So about 2 years ago, NIST, NIST is the government agency that sponsors speech recognition evaluation over the last 20 years or something, and they actually got a few people. So this person used to be a Dragon system. I don't know, everybody used the Dragon. He's a CEO Dragon, and after Dragon was bankrupt, and then some of us actually got together in the Coast House in Washington D.C. in a hotel, and they said that, that was 2007. They said that, well, there is a new DARPA coming up, right? So that was so a security agency will have millions and millions of data available, eventually, that may be maybe used to sponsor this kind of research for large-scale research. Well, it wasn't quite clear exactly how it is. They said, well, why don't we fly you guys down there for 2 days, close the door, don't talk to anybody. Let's brainstorm 2 things. Number 1, identify the milestones of this field over the last 20 years. So we list, what other methods. Number 1 is hidden micro model. Everybody agree. There's no doubt about it. Without this, no progress will be made. And of course, the number 2 factor for this milestone is what's called infrastructure. the availability of very large amount of data, very fast computing, all this. But anyway, and then the next part of this report is to, so this report is called Mind Report. Well, actually, so this is speech is one of those. They actually got 5 areas of people. Each area they got 5-6 experts. So this is called machine translation, information retrieval, natural language processing. This is called document recognition and speech recognition. 5 areas altogether. So we actually put it into the hotel to brainstorm. And then we wrote a report. This is on the web now. Everybody can read it now. And the second part of the report is to describe what is your view of next 15 years of research. So everybody is supposed to give the list. So all of us put that number 1, using human mechanism to do that. And then actually, so it's big trend, working on that. Yeah, of course, there are some other issues that people are looking at exactly how this technology can be done. So anyway, so some of the issues that this is actually written down somewhere. Cognition drives speech models. And the kind of model I talk about, actually, I don't believe is sophisticated enough. So human brain will have much greater sophistication to do all this. And maybe some of the computation had to simplify so that we can enable the model to be done. So that's all I have. Thank you very much.
All right. Thank you very much. So it's getting pretty late, and let Deng make an announcement, and we'll.
Got it.